Hello everyone. Today I'm going to be introducing some basic components of a graph that models the changes in product concentration based on changes in substrate concentration. This is going to be really important to do before we derive the equations so you know what each component of the graph and what each component of the derivation means. We should first define the axes of our graph. Our x-axis is going to be the change in substrate concentration, and the y-axis is going to be the change of the product concentration. Although we have already previously mentioned this in videos, controls that we must have for this reaction is enzyme concentration and, if available, inhibitor concentration. This is because we only want to test the effects of our independent variable, substrate concentration, on the product concentration. Next, we will talk about how we notate each part of the graph. We have consistently used capital letter S to notate the substrate and capital letter S with brackets around it to notate substrate concentration, while we have used capital E to notate the enzyme and capital letter E with brackets around it to notate the enzyme concentration. We will continue to do this while we are deriving the Michaelis-Menten kinetic equations. However, another important variable that we'll be adding is capital P as in product and capital letter P with brackets around it as in concentration of the product. We will be also using I to notate the inhibitor and capital letter I with brackets around it as a concentration of the inhibitor. As mentioned before, there are going to be three types of complexes that can be formed across the different inhibitor behaviors for inhibitor, enzyme, and substrate interactions: the ESI complex, the EI complex, and the ES complex. We will be notating the ESI complex as capital letters of E, S, and I, and then the concentration of the ESI complex with the capital letters of E, S, and I with brackets around them. And we will be notating the EI complex as capital EI, and the concentration of the EI complex as brackets around capital letters E and I. Finally, we will be notating the ES complex as ES and the concentration of the ES complex as the capital letters of ES in brackets. The next thing that we're going to be talking about is Vmax. Vmax is the maximum rate of product concentration formation, or when the graph begins to asymptote or approach a single value, meaning that the slope approaches zero. This is going to be very important for our later derivation of the Michaelis-Menten kinetics. The important thing to note about Vmax is that it is not an intrinsic property of an enzyme, because the Vmax depends on the initial enzyme concentration that is available. For example, if there is a larger concentration of enzyme, the Vmax will be higher because there are more enzymes available to catalyze the reaction. However, if there is a lower amount, there will be a lower Vmax. Thus, it is important to note that for Michaelis-Menten equations, the Vmax will directly correlate with the enzyme concentration present in the model. Another important value that we'll be using throughout our modeling is the Km value, also known as the Michaelis constant. The Michaelis constant, in contrast to the Vmax, is an intrinsic property of an enzyme. The Michaelis constant is a constant that measures the substrate's affinity or ability to interact with an enzyme. If our enzyme reaction can be modeled as this equation above, then our Michaelis constant for this enzyme is determined as this equation. As you can see, the Michaelis constant is determined by adding the K-1 and K2 values over the K1 value. You can think of it this way: K-1 and K2 is the rate of dissociation from the enzyme substrate complex. On the other hand, K1 is the rate of association of the enzyme substrate complex. We're taking the rate of dissociation and dividing it over the rate of association. If the affinity of the enzyme binding to the substrate is very high, then the Michaelis constant will be lower, while if the affinity of an enzyme binding to a substrate is very low, then the Michaelis constant will be higher. Thank you very much for watching this video, and I am super excited to begin the videos showing the derivation of the Michaelis-Menten enzyme kinetics. Thank you.